go. All right, so move this over. So it says the modern atomic theory, and what you're going to find out, the modern atomic theory, it's not as modern as you would think, but in the early 1900s, that's when a lot of this stuff was proposed, and we just simply made it a little bit better. So 100 years ago, and we call it the modern atomic theory. And what was happening is, I don't know if you know, remember Madame Curie, ever heard of her? Her husband, Pierre Curie. They discovered a lot of things with the radioactivity. They found out that the atom was actually made of parts smaller than the atom. Before that, they thought atoms were just kind of like ball-like objects like this. And then they said the atom must be made of something smaller than that, subatomic particles. And that just opened up scientists' eyes. And probably one of the biggest revolutions in all of science happened in the early 1900s. It was mainly in the physics area. And that's where you get people like Einstein and Schrodinger and all these people. If you ever watched the TV show Big Bang, you ever watch that show? Whenever they name drop, it's probably one of those people's name because if you're a physics person, you know that. So the physics people were actually studying the atom. So in a way, it's chemistry. It's like nuclear chemistry. And a huge explosion of ideas came out. And that actually transformed what we thought about everything. And the quantum mechanics model came out of that time. So it's 100 years ago, but we still call it the modern atomic theory. So anyway, so I'll show you some things here. Why would they have a picture of a neon sign? Why do you think that's in here? You say, well, I don't know anything about this chapter yet. Well, it has to do with, I'll show you probably this week sometime. I'll set up a demonstration where I have some neon, and the neon's in a glass tube. And when you look at it, it looks like air. It looks like nothing. But when I run electricity through it, you'll see it'll glow, like Hot Now, pizza, open. Whenever you see a neon sign that glows, if you turn the light off, it's not orange. It just looks like air. And then this is not neon. That's a different gas. They put a different element in there, and when they excite it, instead of being orange-red, it's kind of like blue. And so what you're going to find out is a lot of the discoveries they made about the atom had to do with light. I always think that's fascinating to me because in the Bible, there's many, many things that talk about light. And we don't know everything. When I go to heaven, I'll have to ask all these questions about light. But light seems to be the key to understanding many, many things in science. And when they were studying light, like this kind of stuff, it meant something. They didn't know what it meant at first. Then they figured it out. I'm going to show you that neon, which looks like orange-red. I'm going to give you a thing you put in your eye. And what you're going to do is it's going to split it up into the different colors. You'll find out that there are actually about 6 or 7 colors of light hitting your eye at the same time, which your brain thinks is red-orange. But actually, neon gives off many, many colors. Not every color, only certain colors. So I want to just, we're going to take a field trip to the back of the room here. So if everybody will stand up, I didn't ask permission, but let's go back to the back of the room here. Good. When I set this up later, this thing's always been here all year, but you have to look at it, you didn't know what it meant. But what we do is, for example, you can excite mercury. Matter of fact, the gym, the lights in the gym, if you look at it, look like air is in them. It's actually vaporized mercury. That's why you can't just let those bulbs break mercury on. But there's vapor. So if you were to excite mercury, it would look like a bright light to you, but it actually is made up of these colors here. And so when you use a spectroscope to separate that white light, you'll see that. If you were to look at, let's say, hydrogen. Hydrogen would give a purple, kind of a blue, indigo, and a red. It would only give those colors. Why? Why would it only emit those colors? Why are you emitting these colors? Why does every element give off another fingerprint? I have another poster here if you want to look here. This is done with a really nice, expensive spectroscope. And it's almost like a fingerprint of the elements. For a while, if you thought you discovered a new element, they would try to dissolve it if they could, try to vaporize it, put it in a flame, put it through the spectroscope, if the lines, the exact lines, were different than any other element, they'd say, you might have a new element here. So anyway, what does this mean? What do these colors mean? We didn't know what they meant for a long, long time, but it came up with this quantum mechanics model. Hi, thank you for your filter. I didn't have to pay for gas or driver or anything like that. All right, let's take a look. The first part you're going to see in the chapter is something we had, and I can't remember if it's chapter 4 maybe, but one of the first people, remember J.J. Thomson? J.J. Thomson, I don't know why he had that thing made, but he had this tube made, and it had a metal disc here and a metal disc here, and he had to have somebody who could know how to make a vacuum, and then after you make a vacuum, you seal the glass off. You have to be able to put the electrodes in there. And then you had to have a battery. Somebody had to invent the battery so you could have a lot of electricity flow through there. And when he did, some kind of a beam appeared. And do you remember that story? And there was a beam that appeared, and he actually took a magnet, and you could actually deflect the beam. You could take an electric field, and we found out that this beam was attracted to the positive electric field. So what kind of things are attracted to positive? Negative, right. And so they found out later, we didn't know what they were, but later they were given the name electrons. And so we said, I thought the atoms are like these little hard, like ball-like things. That's what they thought atoms were, but now we know the atom's made of something smaller than the atom, the electron. Well, then Rutherford, he got into it. Do you remember it was called the gold leaf experiment, where he had, I don't know if you remember that. He had some radioactive material that was shooting little positive bullets. You couldn't see them. They're very, very tiny, out of radioactive materials. And he had a screen, and every time those little bullets hit it, it would scintillate. It was actually glow, 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 okay? And so then, if you were to put something really thick in front of that, there would be no glow. Well, he had a really thin piece of gold. It was solid gold, but it was really thin. He puts it in front of the beam, and almost everything, little bullets still went through there, and he couldn't understand that. If the atoms are little balls, then a lot of those balls should have stopped his little bullets, and yet he found that almost all of them went straight through. And that some of them weren't. Some of them got deflected back, or like this. And so that's where Rutherford came up with that's the first time any human thought that the atom had a nucleus. And the nucleus, he said, must be incredibly small. Why? Because almost every bullet went right through the atoms. So he said most of the atom is nothingness. It's empty space. But if I got close enough to a nucleus, the nucleus must be positively charged, because my positively charged bullets would be deflected. Not very often. Some of them deflected right back at me. So the first time that any human thought that the atom had a nucleus, and it was incredibly small, and it had almost all the mass was in the nucleus. Do you remember that story? That was called the Rutherford's atom there. All right, let's go to the next one. And this is not a very good model, because you can't really, to try to do a model size-wise, you wouldn't even be able to see the nucleus. We did that on that other chapter. All right, so now I'm going to jump. I'm going to make a little jump here from the nuclear atom to the study of light. Now, look at this right here, electromagnetic radiation. Has any teacher ever used that with you? Have you ever heard any science teacher use that word, electromagnetic radiation? Because I remember hearing it a long time ago, and I didn't think I knew what it meant, you know? You know what it is? It's light. And so what I'm going to do is I'm going to show you another picture. If you don't have your book with you, just kind of pay attention up here. We have this is called a spectrum, because it's lined up from smallest to biggest, or biggest to smallest. It's a complete spectrum. And what I'm looking at is energy. What kind of energy? It's electromagnetic energy. Now, even though the story behind light was a big problem. People did not know what light was for a long, long, long time. We had debates on it and all kinds of stuff. But I can tell you that we know that light has a property, and around, anytime light flows, around that, there is an electric field and there's a magnetic field. And so what they said is electromagnetic in nature. It's electromagnetic radiation. So electromagnetic radiation is simply light. Can you see here? Maybe I can. Let me go ahead and make this bigger. Whoops. Can everybody see? Can you see those numbers there or not? Okay, so those are in meters, and they have to do with wavelengths. So I want to know, I believe at least one of your teachers should have done something like that. Have you in any of your classes, do you ever study waves? Raise your hand if anybody's ever taught you anything about waves. Okay, all right. So let's take a look. This is a wave, and this is a different wave, isn't it? Now, if you go from the top of that wave to the top of that wave, that's called the crest at the top, get it? Or the trough. If you go from any part of this wave to identical part of the next wave, the distance between here and here is called a wavelength. Now look at this guy here. Look at the wavelength here. Look at the wavelength here. Which one's bigger? The red one, isn't it? So the wavelength, and we found out later that light has different wavelengths. And I'll get back to red and blue here in a minute. So let's go back up here. Okay, so everything you see up here is light. You're going to look at me and say, oh, wait, that says X-rays. That's light. Oh, that says TV waves. That's light. That says radio waves. That's light. And here's the visible spectrum. That's light. You can actually, God said, of all the wavelengths of light, I'm only going to let your brain perceive this much, a little bit. Our brain, I don't know if for whatever reason, maybe you thought our brain wouldn't be able to handle if we could see every kind of light. Like, see that green? If I could see your cell phone waves, it would be some other color. It'd be a new color. If I could see the radio waves from a radio station or a TV station, it'd be another color. And if they turn the microwave on, that would be another color. So we can't see those forms of light. Yes?
How do microwaves even work? Because you open it and it's not hot inside.
Okay, and actually, it's part of this chapter is not about microwaves, but we find out that certain wavelengths, let's say this is a certain kind of atom, okay? Remember that thing back there we went to our field trip? Mm-hmm. Okay, did you know that certain elements, when you hit it with give a certain kind of wavelength, it'll say, well, I'll ignore that wavelength. It says as if it doesn't exist. But other wavelengths, an atom will say, I like that. I'm going to absorb that energy. My electrons are going to absorb that energy, and my electrons are going to go to an excited state. And we don't, that's a great question. For the microwave, here's what happens. Water, H2O, it has certain wavelengths that it'll absorb. And if it absorbs it, it'll make the water go like this. Bounce back faster, 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 faster. That's called kinetic energy. Now, when you use a microwave, the things you're trying to heat up have to have something that absorbs that certain wavelength of microwave. And water does it. So your food almost always has water in it. So what it's really doing is making the water vibrate, which makes the hot dog next to the water vibrate, and that's how your hot dog gets hot, because of water in there. Now, I've seen, have anybody ever noticed that certain cups, if you put it in a microwave, you come out and you don't burn your hand? Have you ever seen some cups? It's like, oh, I hate that. And there must be some materials in some cups that can absorb wavelengths the same that water does, because the cup itself is getting hot. It shouldn't. You can buy things that don't get hot at all in a microwave. They don't absorb any of the microwave wavelengths. But it's mainly the key is water. And if you can vibrate water faster, it'll heat whatever is in next to the water, and that's how they work.
What about hot pockets? How do they work?
Well, hot pockets at water. They certainly have water in them. Now, I'm not a physics teacher, but there's some materials they have called a high specific heat. What that means is it takes a lot of energy to get them hotter, but once they get hot, they stay hot longer. And on hot pockets, for example, some of that stuff in there, it takes a little longer to get that stuff hot, but it'll stay hot for a long time, especially when you got that crust on the outside. It doesn't let the heat escape. You put your mouth in there and you burn the roof of your mouth.
We should go get some
So-
and eat it
Yeah, we should
as
test
an
it.
experiment.
I've done that with, I haven't tested it, but I remember, I don't eat them anymore, but McDonald's used to have these apple pies. And apple pies used to have a crust on the top and the bottom, and you get out there and you touch your fingers, okay, okay, and you get burned. Because the sugary stuff inside there had a high specific heat, and the crust cooled off very quickly, but not the stuff inside there. Now McDonald's makes their apple pies like a zigzag, a lattice. So I think unless some of the heat escapes, so people don't get burned. You know.
They got sued.
They shouldn't have done
But they got
that.
sued with hot coffee. It seems strange to me. It's like, give me some hot coffee, right? And they spill it. Hey, it was hot. I'm gonna sue you because it's hot. Well, I still don't understand that.
Isn't that one too?
Unless I myself poured it on you, I don't see how you can sue McDonald's because
No.
you sport it on yourself. Right?
The person won the thing too.
What now?
The person
I can't
that
believe
sued them
that.
won
Why isn't that a AP
Yeah.
case?
That's for like cost on the side of like the hot.
Yeah, okay, so, I mean, it's kind of weird nowadays. You see all kinds of things with directions, you know. They'll say, do not put that in your mouth. Nobody should ever put, they have to put all kinds of things in there just to try to prevent lawsuits. Hey, all right, let me go ahead, let's go back. Okay, here we go. Let's go back to the story. Now, so everything in this black bar is light. Now, look at this over here. 10 to the minus 12 meters. Now, I don't know if you understand that, but 10 to the minus 9th is a billionth. 10 to the minus 12th is a trillionth. A trillionth of a meter. That means that wavelength is so tiny, I can't even do it with my finger.
What is that? Gamma radiation? Is that Hulk?
Okay, so we're going to talk about the Hulk. Okay, we'll talk about Hulk if you want. So what happened is, so the smallest wavelengths of light that we know are somewhere in the gamma ray area. Now, let's go over here. What are some of the longest wavelengths? And they're actually called radio waves, and some of them are 10 to the 4th. Now, think about a meter. Now, think about 10,000 meters. So the top of one wave and the top of the next wave, 10,000 meters away. Now, that is a really long wavelength, isn't it? They've done a lot of studies showing whales, for example. Some of them communicate, and they use a sound wave that has incredibly long wavelengths. So they can be heard like for miles, like 10 miles in the ocean. If they make a noise, it can go really, really far. Some of these really low, long wavelengths. So anyway, I want to show you these. All of these. Now, which one do you think travels the fastest? You think gamma rays, visible light, or radio waves? Which one do you think is the fastest of them?
Radio.
What do you think?
I think they're the same. Trick
It's
question.
like Hulk was pretty fast. So.
Okay, and we can talk about Hulk in a minute, but anyway, it's kind of a trick question because they all travel at the speed of light.
I knew it. I knew
So
it.
I want you to think about this now, right? Now we're thinking. We're going to think. If all of these travel at the speed of light, then how often would a wave come by? That's called frequency. How frequently would a wave come by? So I want you to think about this, all right? Ready? What if you had an incredibly small wavelength and you're traveling at the same speed as a long wave? Which one's going to have more waves per second?
Good guess.
The gamma. So watch now. Small wavelength, high frequency. Get that? Frequency, how often the wave comes by per second. And then high frequency means high energy. Now I need you to remember that. This whole chapter is based on light. So, and I think I might have a picture in your book. Yeah, here's a picture in your handout sheet if you want to draw on it. And so what we have is, this one's the backwards from the picture in the book, but here's your gamma rays down here. They have really small wavelengths, but they're high energy and high frequency. So, okay, so now, which one of these waves could probably do the most damage to my living cells? Gamma, because high energy. Now, X-rays are up there too, aren't they? High energy, that's high energy light. Now, we actually do use X-rays for lots of things. X-rays nowadays are not as powerful as they used to be. When they first discovered X-rays, they did not know how dangerous they were. They even had, if you look back in history, they even had a shoe store that you could go in, and you always wondered, oh, how many feet? I always get the wrong size shoe. And they thought this new technology would be a great way to sell a lot of shoes. So they advertised that people would come in, and they would stand on this plate, and x-rays would be shot up at them, and they would get a picture of their feet. They say, see, madam, you need a size 7. Sir, you need a size 8, 8.5. And they thought that was the greatest thing in the world. And then later, as they were doing more studies, they said, x-rays are not good for living things. They can cause mutations. They can cause lots of bad things. Now, I don't know what happened to that company. They just kind of left town or whatever. But we were shooting x-rays at people, and we were shooting at a place where if you took a biology class, it doesn't matter that much. If about 100 cells here gets killed, they'll be okay. They'll be replaced. You shouldn't shoot x-rays at my sex cells. Because if you mutate the sex cells and they happen to be the one that fertilized the egg or vice versa, then every cell in that person's body has that mutation. That's bad. Okay? When I hate to talk about this, I hate to talk about it. Humans have done all kinds of bad things. It's okay. If we learn from it, then we're better. If we keep doing it, we're still bad. We know we're sinful. It's just that when we dropped the bomb on Hiroshima, there were 2 of them actually in Japan, a lot of x-rays and gamma rays were given off in this blast. So even though lots of people died in the original blast, even 25 and 30 years after that, there were still babies being born with bad birth defects. Because some of the people who didn't die, they were exposed, and their sex cells were exposed to these things, and a lot of mutations occurred. And so that bomb lasted much more than just that week or that year. 25, 30 years later, it had an effect. All right, so long story short, we actually, though, now, when we take x-rays, we know how to, the sensors now that sense the x-rays, we only need a fraction of the x-rays nowadays. So when a dentist takes an x-ray of your mouth, they're using a really low dosage of x-rays. And when you get your leg x-rayed, they almost always, they'll put like an apron, not over your face, but over the middle part of your body. And you say, oh, I get that now. Anyway, also x-rays are only good at looking at hard objects. So if something's wrong with your stomach, your intestines, x-rays are not going to do any good. So it has to be something like a bone or teeth or something like that. So we actually learned how to use x-rays. Almost everybody in this room knows somebody who's had cancer. They might be going through that right now. And there's different kinds of cancer therapy. One of them is called chemotherapy. Chemo means chemical. That means they're actually taking a chemical, and that's going to actually kill a lot of cells. Now, the chemical goes all over my body, and there's a lot of side effects. And you say, well, they might lose their hair, but it's not they wanted to. And so the chemo goes all over your body. A new type of cancer is where they have chemo and they direct it and they put it in a location and leave it there. They let the chemical be there. They don't let it go all over your bloodstream. That was better. But then another one is called X-ray. Have you ever heard anybody having X-ray therapy? Or they call it, I'm trying to think what they call it in the hospital. Anyway, what they would do is if you had, say, a brain tumor, they would figure out exactly where that is, the length, the width, the depth, like that, and they would actually take, and you could have a treatment that day. You might last for an hour, and they would actually shoot x-rays at that part right behind that skin. And yes, they might kill some good cells with the bad cells, but that's the idea. You're trying to kill the bad cells. And by the way, if you didn't know what cancer was, it's you. It's your cells that don't want to do what they're supposed to do. Something in the DNA has changed, and instead of being a lung cell, I don't want to be a lung cell anymore. I just want to grow and multiply and starve all the other cells around me. And I might even break off and go to another part of your body and do it again. So you are killing cells regardless. And so when they have X-ray therapy, then they are, you might take a dose and you might come back a week later or 3 weeks later, take another one. And what they're trying to do is kill that group of cells there. So anyway, these are high energy, and we've used it for good. We've actually used it for good. Okay, now here, these are really long wavelengths. You said, well, good are they? They're not even that high energy. Well, they actually travel very well. They travel long distances really well. And so what they do is, I remember when I was your age, there's no way, when you said the word radio waves, there's no way I didn't think that was sound. I thought, well, radio, I've heard of radio stations. I thought radio stations gave out sound waves. I was naive. If a radio station gave out sound waves, wouldn't anybody who lived near them be deaf by now? So they don't send out sound waves. Radio stations send out light. They send out light. They're called radio waves. Now guess what's on the radio waves? A code. A code is on the radio waves. They use the radio wave as a carrier wave. I'm going to put a code on that wave. When it hits my receiver on a radio, the receiver decodes it. Get it? So when we want to talk to astronauts who are orbiting the Earth, we don't send sound waves. Our sound waves are changed into light, called radio waves, and they get there like that. By the way, light is incredibly fast. I don't think you ever heard of 186,000 miles per second. So you could go around the Earth, if you got a fiber optic cable, you go around the Earth 7.5 times, ready? 1,001, 7.5 times around the Earth, to the moon and back in less than 4 seconds. And we have done that. We actually have mirrors on the moon, and we shoot lasers right at that mirror, and we have atomic clocks. We measure it very carefully. They said within 10 centimeters, we know the exact distance between the Earth and the moon. Anyway, so light is incredibly fast. Now, I am surprised that humans ever figured out that much as they did about light. Okay. I gotta watch my time here. Sorry. Okay. Hey, thank you. If you want to start reading the first 5 pages, that's what I would do. And tomorrow,